In this application, I want to go over some of the things that we've done in Unit 3. And the idea is to put together all of the estimation techniques that we talked about, and also put that together with the idea of partitioning a data set into the training portion and into a validation portion. So what I'm going to do, I'm going to open this R script that I wrote, application to validation and training. And then the first thing that I'm going to do, I'm going to go ahead and change my working directory to where I saved the data. There we go over here. I'm going to start by cleaning up. I just opened R, so I don't have anything to clean up. And then the next thing I'm going to do, I'm going to go over here and load the data set. We have this data set that's called hitters, and we have salaries for a bunch of baseball players, and then we also have a bunch of statistics regarding their performance. I'm going to look over here at the data set, and baseball is not my thing, but then you see here the explanatory variables. And then if we scroll over, this one over here, the salary, that's the variable that we want to predict. I'm going to just go ahead and check the dimension. So we have 263 observations, and we have a total of 20 variables. So I have my dependent variable, which is salary, which leaves me with 19 explanatory or predictive predictors. And then here I'm just checking again the number of observations in my sample. So the first thing I'm going to do, I'm just going to run a regression model. I'm using the entire sample at this point, and here I'm running a regression of salary. And what I'm doing over here, I'm saying dot, meaning run a regression of salary on all of the other variables that we have in the sample. And then I'm going to look here at the output from this regression. A bunch of those variables are not statistically significant. However, the model taken together is highly significant. So what I'm going to do next, I'm going to split the data. I'm going to do a 50-50 split. I'm going to split it into a training portion and a validation portion. So the idea here is that I can't just estimate this model, and then in order to figure out whether it has a good forecasting performance, I cannot use the same sample that I've used to estimate it in the first place. So what I need to do is estimate it, the model on a training portion, and then in order to figure out the forecast performance, I have to use the validation portion of my sample. So in other words, I have to see how good of a job my model is doing on the validation data, which is a data set that the model did not see, was not trained on in the first place. Now, because I'm doing a random split, so I'm randomly selecting, 50% of these observations, I'm going to set the seed just to make sure that the results are tractable and all of us obtain the same results. And if we run this again, we can look at the same results again. So what I'm doing over here, I'm selecting the rows that are going to be used in the training sample, and then I use the function sample, and I'm just telling R, hey, select 50% of the observations that we have in the original data, and those are going to be the rows that are selected for the training data. And then I create a data frame where I save those observations into the training data. And then if you want to look at it, you can go over here and see the observations that were sampled and what we have in the training portion of the sample. And then I'm going to go ahead and set diff is looking at all of the remaining rows that were not selected for the training. So everything that wasn't selected in the training sample, it's going to go ahead and it's going to be marked for the validation sample. And then I go ahead over here and then I create a data frame where I have, here it is, where I have the validation portion of my sample. So I have 131 observations in the training sample and then 132 for validation. So then here is what I'm going to do. I'm going to first start with regression, then I'm going to do ridge, then I'm going to do lasso, and then I'm going to do principal component. And then for each one of these models, I'm going to estimate the model on the training set. Then I'm going to use those values I obtained on the training set in order to make predictions or forecast on the validation part. Then I'm going to calculate the forecast error, which is going to be the difference between the actual values for salary in the validation sample and whatever I predict those values to be with my model. Those are going to be the forecast errors. And then I'm going to come up with a measure to quantify on the entire validation sample on the average what's the forecast error. And then I'm going to compare these forecast errors across these models. So I first start with regression and notice that I fit the exact same model I had before, but now instead of selecting the entire sample, I'm only estimating the model on the training data. Go over here and I can look at the output from this model, and then what I want to do, the first thing I'm going to do, I'm going to create a data frame where I'm going to save in this data frame the actual values in the training sample for the salary, what I predict the values to be with my model, and then I'm also going to save in there the residuals, which are the forecast errors. Now, of course, these are going to be the forecast errors on the training sample. I can't use those in order to evaluate the forecasting performance of this model, but let's just look at them just to have an idea. And these are 6 observations in the training sample, and these are the actual values for salary. This is what we predict with the model. These are the errors. Now, of course, again, we need to do all of this for the validation sample, not for the training sample. So then what I want to do, I'm going to predict. Now notice that I use the results that I've saved over here. So I fit this model over here and I save the results with this name, fit train. And so I'm using the estimates from the training sample. But then when I predict, I'm going to predict using the X values, using the predictor values on the validation sample. And then the residuals, which are the forecast errors. These are the difference between the actual values for the salary, again in the validation sample, minus what I just predicted. So obviously if there's an error, the difference between the actual value and what I predict, that's going to be my forecast error. And then I'm going to create another data frame, but on this data frame I want to save the actual values, the predicted values, and then I want to save the forecast errors for the validation sample. And again, let's just look at a couple. Oh, I forgot to run this. So let's look at a couple of observations. So here is the salary. Here is what we predict the salary to be with our model. And then here are the residuals. So then ideally, what I'm going to do, I'm going to look at these residuals, at these forecast errors, and I want to come up with a measure that tells me on the average. So remember that we have 132 of these residuals of these errors in the validation sample. I want to come up with one number that tells me on the average what's the forecast error associated with a linear regression. So if you're thinking about how I want to construct this, one thing I could do, you're probably thinking, let's just average all of those errors. That's a good idea in theory. In practice, what can happen is that I can have a large positive error, a large negative error. They're both large, but when I add them up, they cancel each other out, and I end up with 0 and a small forecasting error, although both of those errors were large to begin with. So instead of averaging the actual errors, a better thing to do is to square those errors and take the average of the squared errors. There's other measures that you can use, and in the upcoming lectures in Unit 4, I'm going to go over a bunch of these measures. For the time being, this is what I'm going to use. It's called the mean squared error. So I square the errors, I add them up, and I take the average across the validation sample. Instead of doing this manually, I'm going to use the library forecast, and then I'm going to use this function over here, accuracy. Before I use this function, I want to make sure again that I predict from the correct model, and because I'm going to compare these errors across a linear model, a linear regression model, a ridge model, a lasso, and principal components, I want to save them such that I can go back and compare the values. So I'm going to call the predicted values from the linear regression pred underscore LR. So again, I just predict using the values, the estimates from the training sample, but using the data for the validation. I'm gonna run this, and then, oops, what did I do? I'm going to go ahead, here I am, I'm gonna go ahead and compare the actual values over here for the validation data and what I just predicted. And the value that I'm going to look at is this one over here, root mean squared error. So we take the squared errors, we average them, and then we take the square root of that number. Now, this is the first model that I've estimated. I have nothing to compare this number against. So I'm just going to make note of it, and then I'm going to come back after I've estimated a couple of other methods and then compare and see if any other method gives me a smaller error on the average compared to this linear regression model. So the next thing I do, I apply the exact same thing for ridge regression. So this is the function, the library that I'm going to use in order to estimate ridge. And now remember, for ridge, you have to give the data a little differently compared to regression. So the x values have to be as a matrix. And I do this a little differently here. In the other example, I was using the function as matrix, whereas here I'm saying model matrix. So I'm saying, hey, run a regression of salary on all of the explanatory variables, and then save those explanatory variables into this x value. Notice that I'm using the train sample, and the -1 stands for the fact that when you look at those regressors, don't include the intercept, because I only want the x values. And then I also save y. Again, notice I'm using the training portion, and I'm saving the y values over there. So I don't think I ran this one. This is x, and then this is y. Now, remember, when you do ridge regression, one of the things that you have to do is you have to figure out the value of lambda. And the way we do that, we perform cross-validation in order to find the value of lambda. So I'm going to set the seed again in order to make sure that everything is tractable. And then over here, I'm doing cross-validation. Notice I'm using alpha equal to 0. So when you use a value of alpha equal to 0, you're estimating ridge. And when you use a value of alpha equal to 1, what you're doing, you're estimating lasso. I want ridge over here. And then what I'm going to do, I'm going to plot. So this is the cross-validation error. And then here are all the possible values for lambda. So what we want is to choose the smallest value of lambda, the value of lambda that minimizes the error across the cross-validation. And what I'm going to do, this is where that value is saved. And I'm going to save it in a variable called best lambda. And this is the value that we get over here. So now, after I've calculated that, after I figured out the value of lambda, I can go back and estimate a ridge regression model. This is the value of x and y that I've selected earlier. Remember, both of them for the training sample. I choose alpha equal to 0 because I want to do ridge. As value for lambda, I choose this value over here. That I just got that value doing cross-validation earlier. Now, standardize equal to true, we've talked about this in the notes. you want to run this regression on standardized data on the z-scores in order to make sure that there is not any measurement units that might affect the estimates. So I'm going to run this, and then now I have the estimates. So I have the estimates from the ridge regression on the training data saved over here in this variable over here. And now I'm going to select the validation portion of the sample. So I'm going to select all the x values, the values that x takes on the validation data, and then I'm going to do the same for y. And I did not run this. Here it is. So these are the x values for the validation sample. These are the y values. So what I want to do, I want to predict using the estimates I got earlier, using the value of lambda that I obtained over here, but I want to predict for the values of x that I have on this validation sample. And then I'm going to do the same thing. I'm going to use that same library forecast. I'm going to save the predicted values from ridge in this variable called pred_r. And then I'm just going to compare, okay, how well does the model perform? These are the forecasts from the ridge model, and these are the actual values of y. So the root square mean error in this case is 373 point something. So what we can do is go back over here where we had the linear regression model and run this line of code again, so we have them next to each other. So now I can see that the mean squared error, the root mean squared error for ridge is 373. The root mean squared error for linear regression was 410. So I do see a forecast performance improvement in the ridge compared to the linear model. So what we're going to do next, we're going to apply lasso. Lasso is very similar to ridge. The only difference is that instead of setting alpha equal to 0, we're going to set alpha equal to 1. Of course, the way that the lasso performs the estimation is completely different. If you remember, for ridge regression, we are shrinking those coefficients, but none of them is actually equal to 0, whereas in lasso, some of those coefficients are going to end up being actually equal to 0, so we can also use lasso for model selection. So exact the same thing that I did before. I save x and y, and I'm using the training portion of the sample. And then I'm going to have to perform cross-validation again in order to find the value of lambda. But notice that now I use alpha equal to 1 because I want to perform lasso. And then this is the value of lambda. That's the best value. That's the value of lambda that is minimizing the cross-validation error. So now I go over here and I estimate, and this one over here should be estimate lasso. Okay, I'm going to save this. So I'm going to estimate using lasso, and I choose alpha equal to 1 in order to do lasso instead of ridge. I select the value of lambda that I obtained earlier from cross-validation. Again, I standardize the data. There we go over here. And then same thing. Select now, save the x values on the validation sample, save the y value on the validation sample, predict using lasso on the new validation sample, and then look at the forecast performance for this model. So this is what we got using lasso. And then I think ridge was a little smaller, very comparable. There we go. So 379 is the root mean squared error using lasso. 373 is the root mean squared error using lasso. I'm sorry, using a ridge regression. So ridge does better than lasso, although they're pretty comparable to each other. However, both of them outperform what we had in the case of the linear regression. If we go back here, now we can compare the three of them. So see, for linear regression I had 410, and then this one over here was Ridge 373, and this one over here is Lasso. So while these two are comparable to each other, the errors in the case of the linear model are higher compared to both of these models. And then the next thing I'm going to do, I'm going to apply principal components. So I'm going to use cross-validation in order to figure out how many components to use in the model. So if you remember, the library PLS can do that for us. Again, it's cross-validation. I'm going to set the seed, and then this is where we perform cross-validation in order to obtain the number of principal components to use. And over here, I can have a summary of running principal components. What I really care about right now is how many components I want to use. So one thing that I could do, see over here, is the cross-validation error, and I could look at the cross-validation errors across all of these models, but there's a lot of them, and I would have to figure out, I mean, it's doable, but I would have to figure out which one is the smallest number of principal components. Instead of doing that, I'm just going to use R to obtain that value instead of just checking all of those values. So I save over here the cross-validation error, and then here I look across all of those errors. I'm looking at which one is the one that is the smallest. Give me the index for that one, and I subtract 1 over here, because notice over here, when you look at all of these models, what R is doing, R is also including a model where we just have the intercept. So that's why I'm subtracting the 1 over there, and it turns out, here we go, that the number of principal components that we want to use is 5. So then what I'm going to do, I'm going to go back and now estimate this model using 5 principal components. So I'm using the X value for the validation sample, and then I'm using also over here. So what I'm doing, I'm using the X values on the validation sample in order to figure out how many principal components to include. I'm using that value that I've created, that I've obtained earlier by running cross-validation. And notice over here that I'm using the estimates that I had earlier when I've used the train data. So basically, I'm predicting using the estimates from the train data, but I'm predicting on the validation data. And then those are the predicted values, and of course we also need the actual values in order to compare the two. And then over here, notice that the root mean squared error, is 377.9. So what I do right at the end, just so I don't have to go back and forth through the code, I'm gonna rerun those forecasting performance measures for all of the models that we considered. So if you remember, the first one over here was for linear regression, and this was 410. Then we had over here Ridge. Then we had over here Lasso. So Ridge did better than Lasso. Now notice that here principal component is doing a little better compared to Lasso. Very, very comparable with Ridge. See, 373.998, and then here I have 377, and then here 379. So actually, these through the Ridge, the Lasso, and the principal component, I would say they're pretty close to each other. All three of them definitely outperform the linear regression ones. So this was an example where we saw how it's useful and it's a good idea to partition the original set, the original data set, into training set and a partition set, and then the idea is that you have a bunch of competing models, and then you estimate each one of these models on the training part, you predict on the validation part, and then you calculate the forecast error for each one of these models, and then you compare the forecast error across all of these models in order to choose one of these models.